Hello students, welcome to 8th lecture of Electrochemistry. So in last lecture we were discussing about the conductivity of electrolytic solution, and we discussed about resistivity and conductivity. Now let's discuss further. Now today's topic is measurement of conductivity of ionic solutions. So in this topic our target is to find conductivity of electrolytic solution. For solid substance, we can use Wheatstone bridge. We can connect our unknown compound or substance with Wheatstone bridge, and then we can calculate the resistance, and from the resistance we can calculate conductance of our sample. But with solution or with liquids we have two problems. First, when using DC current, it can change the composition of used solutions. That means suppose you have CuSO4 solution or NaCl or ZnSO4 solution, it will change the composition, and it will give us oxidation or reduction reaction. That means our solution can't be pure, it will participate in reaction. So we can solve it by using AC current. But second problem is, just like solid piece of wire, you cannot connect our solution with Wheatstone bridge. So to overcome the second problem, we can use specific devices called conductivity cell, which can be used to find the conductivity of unknown solutions. Two examples are mentioned here. In this case, we have two different electrodes in both of the conductivity cells connected with external batteries. Okay, so that means we can place batteries here, and we can fill liquid inside the container from special inlet valves. Okay, and then we can pass the electricity and we can measure the conductance or resistance. Distance between two electrodes will be called L, and volume of our solution will be called V. Later we will discuss about V. So in our cell we have two platinum electrodes coated with the platinum black. Again remember, just like platinum used in the cell, we are using same type of material here because we do not need electrodes to be participated in the reaction. Okay, we do not need any kind of side reaction. That's why we are using platinum, which is inert and do not participate in reaction. This electrode have area of cross section equal to A and thus separated by the distance L. Therefore solution confined between these two electrodes is a column of length L and area of cross section A. So just like a solid substance, as mentioned earlier, conductivity and resistivity, they are directly related with length and area of cross section. Resistivity is directly proportional with length and inversely proportional with area, and opposite is true for conductivity. Conductivity is directly proportional with area of cross section and inversely proportional with length. So for resistance you can get same type of equation as we discussed earlier. R is equal to rho into L upon A, or R is equal to L upon kappa into A. Now L upon A is called constant because it do not change for given cell. Okay, so it is cell constant, and cell constant can be denoted by symbol G star. It depends on the distance between the electrodes and their area of cross section, and has the dimension of length inverse, and can be calculated if we know the L and A. That means you can practically measure the distance between two electrodes and area of their surfaces. So that means we can manually calculate the cell constant, and if we know the cell constant, then our calculation will be quite easier. And for simplicity, in most of the cases, length and area of cross sections are unity. That means distance between two electrodes will be 1 centimeter apart, and area, surface area of the electrode will be 1 centimeter square. That means cell constant will be 1. So it will be easier to calculate the resistance or conductance if constant is equal to 1. But measurement of L and A is not only inconvenient but also unreliable. That's why we have to use reverse approach. First of all, we will use some known solution. Okay, that means known quantity of resistance for given solution, we will fill that in the solution, in the cell, and then we will find the L upon A, that means cell constant for given cell. And for this purpose, we generally use the KCl solution whose conductivity is known accurately at various concentrations mentioned in table 3.3. And the different temperatures, the cell constant G star is then given by the equation G star is equal to L upon A, or it is equal to R into K. Now, different concentrations and conductivity values are mentioned in this table. You can see it. Once the cell constant is determined, we can use it for measuring the resistance of conductivity of any solution. The setup for the measurement of resistance is shown in figure 3.5. Okay, so as we can see, this image almost look like Wheatstone bridge. At the center we have detector, and we have different resistance R1, R2, R3 and R4, where at R2 our conductivity cell is attached, and then we can see the values in detector. So our instrumentation consists of two resistance R3 and R4 and a variable resistance R1, and the conductivity cell having the unknown resistance R2. The Wheatstone bridge is fed by the oscillator O, a source of AC power in the audio frequency range up to 550 to 5000 cycles per second. Okay, so we can manage it as per our requirement. P is suitable detector, a headphone or other electric device which will give us either light indication or volume or sound indication, so that we can find the value. And the bridge is balanced when no current passed through the detector. At that time we can find the unknown resistance using the equation given below. R2 is equal to R1 into R4 divided by R3. But nowadays we have inexpensive devices which can give the direct value of conductivity or resistivity. Once the cell constant and resistance of the solution in the cell is determined, the conductivity of solution is given by the equation K is equal to cell constant divided by R, or G star divided by R. We are using the same equation, nothing is different in this case. The conductivity of solution of the different electrolyte in the same solvent and a given temperature differs due to the charge and size of the ions in which they dissociate. The concentration of ion or ease with which the ion move under the potential gradient, it therefore becomes necessary to define a physical more significant quantity called molar conductivity, denoted by the symbol lambda m. It is related to the conductivity of the solution by the equation lambda m is equal to kappa upon C, where C represents concentration, K represents conductivity. Now keep in mind, we are using the new symbol or new conductivity value because different solutions has different type of dissociation units or dissociation percentage. Not all of them dissociates 100%. Some of them dissociates very poorly. Dissociation, that means when we dissolve, as for example NaCl into the solution, it produces Na plus and Cl minus ions. But not all of the NaCl dissociates in positive and negative ions. Some of the molecule will still remain in molecular form, and these molecules do not conduct the electricity. So different solutions, different electrolytes gives different amounts of ion. That is our first problem. Second problem is, same type of electrolyte gives different type of percentage of dissociation with different type of concentration. Usually higher concentration gives lower percentage of dissociation, and at lower concentration dissociation percentage increases. That means suppose you are using 1 molar solution of NaCl, and this 1 molar solution gives 80% dissociation. That means out of 1 mole 0.8 moles will dissociate. Now suppose you have 0.1 molar solution of NaCl. So lower concentration will increase the dissociation percentage. At this concentration, let us say 0.09 moles will dissociate. That means it is 90% dissociation. So suppose you are using same quantity of NaCl in two different concentration. That means we have 1 molar and 0.1 molar solution of NaCl. But in both of them, quantity of NaCl is 1 mole. That means 1 mole dissolved in 1 liter and 1 mole dissolved in 10 liters. So 1 mole dissolved in 1 liter is 1 molar solution, and 1 mole dissolved in 10 liter is 0.1 molar solution. So in first solution 0.8 moles will dissociate, but in second solution 0.9 moles will dissociate. So same quantity of NaCl gives different number of ions under different concentration. So that's why we are moving on molar conductivity value, which gives us constant results. Now in the above equation 3.21, if kappa is expressed in S meter inverse and the concentration C in mole meter minus raised to minus 3, then the unit of lambda m are S meter square mole inverse. It may be noted that 1 mole meter raised to minus 3 is equal to 1000 liter divided by m cube. So molarity mole per liter, and hence our equation will be, now with unit same equation is mentioned. Unit of lambda will be S centimeter square mole inverse is equal to kappa S centimeter inverse divided by 1000 liter divided by m cube multiplied by molarity. If we use S centimeter raised to minus 1 as the unit of K and the mole centimeter raised to minus 3 the unit of concentration, then the unit for lambda m, it is not em, it will be lambda m, are S centimeter square mole inverse. It can be calculated by using the equation as mentioned follow. So you can derive the unit from the given equation, and these equations are related to each other and both of them are being used regularly. Now some examples are mentioned. First is resistance of the conductivity cell filled with 0.1 mole per liter KCl solution is 100 ohm. If the resistance of the same cell when filled with 0.02 mole per liter KCl solution is 520 ohm, calculate the conductivity and the molar conductivity of 0.02 mole per liter KCl solution. The conductivity of 0.1 mole per liter KCl solution is 1.29. So let us quickly discuss our example. So the value of conductivity of 0.1 molar KCl solution is mentioned 1.29, and KCl solution, for the same KCl solution resistivity or resistance is also mentioned. So from these two values we can calculate the cell constant, which is 1.29. Now using the value of this constant we can find the next value, conductivity of 0.02 molar KCl solution. It will be cell constant divided by resistance. So cell constant 129, resistance 520, which is mentioned in our description. So it will be 0.248 as meter inverse. Then concentration is 0.02 molar, and it is equal to 1000 multiplied by 0.02 moles, which is equal to 20 moles per meter cube. Now molar conductivity lambda m is equal to kappa upon C. So value of kappa as calculated earlier, it will be 248, and concentration is 20 mole per meter cube. So it is equal to 124 into 10 raised to minus 4. Or secondly, kappa is equal to 1.29 divided by 520, it is equal to 0.248, and lambda is equal to K into 1000 divided by molarity. So it will be 0.248 multiplied by 10 raised to minus 2 multiplied by 1000 divided by concentration 0.02, it is equal to 124 again. Okay, so you will get the same value with variable unit. Second example, the electrical resistance of column of 0.05 mole per liter NaOH solution for diameter 1 cm and length 50 cm is 5.55 into 10 raised to 3 ohm. Calculate its resistivity, conductivity and molar conductivity. So given values represents cell constant, that means length and area of cross section. So we can use the values in our direct equation of R or resistance. So R is equal to rho into L upon A. That means rho is equal to R into A upon L. So resistance is 5.55 multiplied by A value, that means area of cross section, which is calculated using the diameter, which is 1 centimeter, so radius will be 0.5 centimeter. For a area of the circle, we have pi r square. So pi 3.14 multiplied by 0.5 square, which is equal to 0.785. So value of area of cross section will be 0.785 divided by length as mentioned 50 centimeters. So rho is equal to 87.135 ohm centimeter. So conductivity kappa is inverse of rho. So it will be 0.01148 and molar conductivity is lambda m is equal to kappa into 1000 upon concentration. So it will be 229.6. Now if we want to find the values in term of meter instead of centimeter, then what will happen? So some values will change, order of 10 will change, so same type of values will be used, but instead of centimeter we are using meter unit, so obviously we have to put some changes in it. So rho is equal to 87.135 into 10 raised to minus 2 ohm per meter and kappa will be 1.148 centimeter per meter, Siemen per meter, and lambda m is equal to 229.6 into 10 raised to minus 4. Now if you find any difficulties in these equations or calculations, feel free to ask, we will discuss them in brief, but right now they are already mentioned properly in these examples, that's why we are not using step by step process. Okay, so if you still find any confusion, feel free to ask, we will discuss these points in detail. Now our next point will be the variation of conductivity and molar conductivity with concentration. This point is already discussed in one of the previous lectures, competitive electrochemistry. So you can refer it, otherwise we are going to refer this point again quickly in short, because brief description is already mentioned in one of the unit of electrochemistry, competitive electrochemistry. So in next video we are going to discuss this point quickly, and I will put a link of that video in which this point is discussed in detail. Thank you.